Okay, so good evening. Uh, this is our 14th lecture, and in the previous lecture, we discussed about the potential flow past spheres. Today, we will discuss about slow viscous flows past spheres. So, little bit idea I already gave you in the previous class that if we have our Reynolds number of the flow very small in comparison to 1, it means viscous forces are significant in comparison to the inertia forces, then particularly the advective terms of the momentum equation can be avoided, and we can simply write that pressure gradient, particularly the modified pressure gradient, is directly equal to the viscous forces. Okay, here the definition of modified pressure is included over here, and once we take the divergence of this equation, then we get Laplacian of modified pressure is equal to 0, and once we take the curl of this equation, then we get Laplacian of rotation field is equal to 0, and ultimately rotation can be written as minus Laplacian of stream function, and this gives from this point to this point that I have biharmonic equation where delta 4 psi is equal to 0. So ultimately, if I have creeping flow or Stokes flow, these are the names which are given for Reynolds number less than 1, and if this flow is actually over a sphere, then I can simply use the axisymmetric assumption, and under this assumption, because I can utilize the stream function, so upon using the stream function, my this single equation will be actually applicable as a replacement for the momentum equation, and continuity will be satisfied by default. Okay, so now this equation we will try to apply for a rigid spherical particle. So it means when I am talking about the rigid particle, I am particularly referring to a solid particle, because if I have a fluid particle, that will be of course always a deformable particle, that will not be a rigid one. So that's why first whatever the analysis I am proposing over here, that is actually applicable for a solid particle, because that will be only a rigid one. Okay, so our domain is the same as we used in case of potential flow, that this is our rigid solid particle, and at the center of this particle I have fixed my coordinate system. So this is radial direction and this is angular direction, and the corresponding velocities are ur and u theta, and a is actually my radius of the particle. So r equal to a signifies the surface of the particle, so it means my radius of particle is actually a. Okay, and again I can have two scenarios. One scenario will be that I have infinite fluid medium which at sufficient distance away from the particle is actually coming at free stream velocity u and moving over a fixed particle, or second situation can be that my fluid domain is actually stagnant and particle is moving with velocity u. Okay, so both the things will be giving me the same type of solution. And considering the steady incompressible flow situation, the corresponding values for radial and tangential velocities in spherical coordinate system can be represented by using these particular two forms in terms of the stream function. Okay, and now this is my detailed extension of the equation del 4 psi is equal to 0. Okay, so you can see here I have second derivative with r and theta inside, and then outside I have square, which will be making nothing but Laplacian of delta 4 of psi is equal to 0. So this is my momentum equation. Now I need to supply the sufficient boundary conditions to this momentum equation, and of course my equation is purely in the form of psi, so that's why the boundary conditions are to be also supplied in the form of psi. Okay, so to supply boundary conditions, my first boundary condition will be, because now I have a solid sphere and I am considering the viscous effect into account. So once viscous effect is considered into account, it means I will be having existence of no slip boundary. Okay, so if I have no slip boundary condition, that signifies that tangential velocity to this surface will be equal to 0. So if you see, tangential velocity to the surface will be nothing but u theta at every point. So if you substitute u theta equal to 0, it means del psi by del r will be equal to 0. Okay, and then we have a solid particle. So because of the solid nature of the particle, there will not be any fluid penetration through the interface. So that's why my velocity in radial direction, this is radial velocity, so this is normal velocity. So because of the solid impermeable boundary, this ur is also 0 at r equal to a. So that's why at r equal to a, I can simply write del psi by del r and del psi by del theta are nothing but equal to 0. Okay, and what will be happening as I am moving at sufficiently away from this solid sphere, so of course there my fluid will be having the velocity equal to u, and velocity u first can be converted in the form of, earlier also I told you, it can be first converted in the form of ur and u theta, and once it converted in the form of ur and u theta, then I will be getting two different boundary conditions. That first boundary condition will be when r is infinity, then what is the value of some known value, C1 value of ur, and second is when r is infinity, then other value of u theta is say some other constant C2, and of course this C1 and C2 are nothing but these will be in the form of functions of u. Is this one clear? Which are coming from the trigonometric relation. So now using these two boundary conditions, if I replace ur with this and u theta with this and then integrate, then ultimately I will be getting my complete boundary condition as psi approaches to half ur square sine square theta plus constant. Okay, so it means that two boundary conditions are applicable. So these two boundary conditions are coming at the surface of the sphere, and these two boundary conditions are coming from the at radial distance sufficiently away from the sphere. Okay, and these two boundary conditions then finally can be written particularly in the form of this psi. Okay, so it means that my equation was having highest order of 4. So I have specified the sufficient 4 boundary conditions here. Okay, so if I solve this particular equation along with these two boundary conditions, then I will get my solution for psi as 1 by 4 u a square sine square theta a by r minus 3r by a plus 2r square by a square. So you can simply say that psi is becoming a function of r and theta. So it means in this equation, if I substitute different values of r and theta, then I will be able to determine the value of psi at my entire portion around this sphere, and then if I join all the values with constant value of psi, that will be giving my streamlines. Is this one clear? Now, if you have got the value of this function psi in terms of r and theta, then you can take the derivative of this particular del psi by del theta, del psi by del r, and then you can determine the corresponding values of radial and the tangential velocities. So now you can see these radial and tangential velocities are also nothing but the function of r and theta. So at different values of r and theta, you can you have now the velocity field known. Once you have the known velocity field, now can you tell me how to determine pressure field? How to determine pressure field? Continuity equation? No. Continuity equation is, we are not solving, that is by default satisfied for stream function. So if I know these velocity field, can you tell me how to determine now the pressure field? Because this is a viscous medium, I cannot apply Bernoulli equation here. So that is applicable for inviscid medium, irrotational flow. Momentum equation, yes, correct. So if you now go to your original form of momentum equation, so what was it? Original form of momentum equation was having mu times Laplacian of velocity field in the right hand side, and in the left hand side it is nothing but gradient of the pressure field. So if you know this velocity field, it means your right hand side is actually known to you. So once right hand side is known to us, then we can simply calculate the left hand side. Is this one clear? So by using the original momentum equation, you can actually calculate the value of pressure field, and if you calculate the value of pressure field, it comes out to be P infinity minus 3 mu A u divided by 2r square into cos theta. So again you can see your pressure is nothing but a function of r and theta. Okay, so because our entire system is in r theta coordinate, so at different values of r and theta I can also predict the value of pressure as well. Okay, this time one distinction from the potential flow theory, you will be finding that here this pressure is nothing but an even function. Okay, so because of this, what you will be finding, that pressure at this portion and so in this sector and in this sector will be actually different. Same or different? So this is an odd function, not even function. Okay. Cos theta from 0 to 90 degree it will be positive, and 90 to 180 negative. Okay, so because of this odd function, you will be finding that you will be having different values of pressure in upstream and downstream direction. Okay, so once you have different values of pressure, it means you will be experiencing a net force because of the pressure term. Okay, so which we call as nothing but our form drag. Okay, so now this pressure will give you which type of drag force? This will give you nothing but form drag. And we have one more drag force. What is that? That is nothing but skin friction drag or viscous drag. Okay, so to calculate viscous drag, what we need to do? We need to calculate the wall shear stress. Okay, so in order to calculate the viscous drag, what we need to do? We need to calculate the shear stress, wall shear stress. So of course in this case I can simply say wall shear stress. Otherwise, if I use the nomenclature of the multi-phase flow, then I should call this as nothing but interfacial shear stress, because this is a particle and this is the fluid. So this boundary is interface in between the fluid and the particle. So I should know the interfacial shear stress. So interfacial shear stress will be tau r theta, and for a spherical axisymmetric flow, this is equal to, particularly for Newtonian fluid, this is equal to mu times 1 by r del u r by del theta plus del u theta by del r minus u theta by r. So if you do calculate this, this comes out to be, so this is my shear stress. Okay, if in this shear stress I substitute that my value of r is equal to a, then this shear stress will be coming nothing but at the interface. Okay, so using the value of this interfacial shear stress as well as the pressure term, what I can do? If I integrate pressure, and so say I have some pressure distribution at this surface, my pressure distribution is something like this. Say this is my pressure distribution. It will be coming entirely on the entire structure. Say this is my pressure distribution. So what will be happening? Pressure at every point is varying at different values of r and theta, and I know how pressure is varying. This function is nothing but a function of r and theta. Now if I take this particular value at any elemental area, so if I take dA as some elemental area, and corresponding to this elemental area, if I take the value of pressure and then I take its component parallel to the flow, because right now I am trying to calculate the drag force. So when I will be calculating the drag force, I will be considering the component parallel to the flow direction. Okay, so parallel to the flow direction, I will be having component of pressure as nothing but value of pressure at R equal to A cos theta times elemental area dA. Okay, and I am doing this integration from 0 to pi. So for half of the portion actually I am doing. Then similarly, so this portion is nothing but giving me my value of form drag. Then similarly I need to do the integration of the interfacial shear. So interfacial shear multiplied by its component in the flow direction actually multiplied by area, that will be giving me nothing but my skin friction drag or viscous drag. Okay, and typically this elemental area dA over here, you can see what is the area of a circle? Pi r square. Okay, and when it is considering this dA elemental area, what we have done? We have written over here 2 because we are doing this integration from 0 to pi. Okay, so that's why this is the corresponding area in the parallel to flow direction, and ultimately my drag force will be coming from here. So F is nothing but a total drag force. Okay, so total drag force comes out to be 4 pi mu UA, where 4 pi mu UA is nothing but the viscous drag component and 2 pi mu A is our actually pressure drag component, and total drag will be 6 pi mu A. Okay, so if you do this integration, because you know the pressure distribution and the shear stress distribution, then parallel to flow direction, if you take the force component by multiplying it with area and then integrate, then you will be finding this to be your drag force. Okay, so this particular result, whatever we have calculated, this result is applicable only for solid particles. Okay, now what I can do, I can write drag force from our fundamental fluid mechanics understanding. How we write drag force? Fd is equal to Cd times drag coefficient times half rho free stream velocity square times area. Okay, so if I have a spherical particle, projected area in the flow direction will be nothing but my area of circle, pi a square. So from here I can write Cd is equal to 2f divided by rho u square into pi a square. So you have the value of f as nothing but 6 pi mu ua. So if you substitute this value 6 pi mu ua and define your Reynolds number as rho u into 2a by mu. So if you take diameter as your length scale for estimation of the Reynolds number, then you will be finding your drag coefficient to be 24 by Reynolds. Okay, and now what we need to do, we also need to estimate that if in the flow field, I am saying that particle, either fluid or particle, is moving actually at constant velocity. So ultimately what is happening? Particle is not having any inertia in the creeping flow situation. So only forces which will be coming into account are driving force and the resistance force. And resistance force is because of the pressure and the shear stresses, which is coming as drag force. Okay, and the driving force for the particle will be nothing but its weight. Okay, so if I do the balance of weight and the drag force, so weight is, what will be the value of weight? 4 by 3 pi a cube into density of the particle, but ultimately density of fluid is also coming into picture. So I have to take the buoyancy force. So when I will be doing the buoyancy force, I will be writing delta rho into G. So this is the net driving force. When this net driving force is equal to the net resistance force, which is nothing but 6 pi mu AU. So once I do the balance of these two forces, then ultimately what I will be able to calculate, this will be U of particle. Okay, so ultimately this will be u of relative in between the fluid and the particle. So ultimately what I will be calculating from this, that my terminal velocity of the sphere is nothing but equal to having this formula. Is this point clear?
सर ये 6 by mu a6 जो निकाला था फ्लो की डायरेक्शन में फोर्स
सर अपर हाफ में आया था 6 by mu अपर हाफ में आया था 6 by mu अपर हाफ 0 to pi.
No, in area I have used 2 as multiplier. Okay, so when I have explained you the area, there this 2 multiplier was used. So this 2 multiplier was used to account for upper and lower both halves. Okay. Yes, this is in the flow direction. So velocity also, when I am saying this terminal velocity, so it is in the direction of the flow. So of course, what you can do, you can say that your flow is happening in this direction and this weight is also acting in this direction. So this is just a reorientation of the figure. What I am saying is, let me tell you again. Okay, so this is the flow, fine, and when you are calculating the drag force, it is in which direction? It is in the direction of force. This point is clear? Is this point clear? Okay. Now, for this type of situation, what I have done? I have calculated the drag force formulation. Okay. When I am defining terminal velocity, then what I am saying, that I have a stagnant fluid. Is this point clear? I have a stagnant fluid, and in that stagnant fluid my particle is actually moving because of the gravity field. So once particle is moving in a stagnant fluid because of the gravity field, say particle's velocity is uts. Okay, so in this scenario, whatever drag force particle will be experiencing, that will be 6 pi mu au, but in place of this u I will be having uts. Is this point clear? So I am making analogy from this to free fall situation of a particle. Okay, is this one clear now? Are you clear with this idea? So here this uts, this is the free fall velocity of the particle, which is uniform velocity. When particle is falling, say if you have an infinite fluid medium and if you drop particle at t equal to 0, so first particle will be having some accelerating mode, and after that it will be achieving the constant velocity. So I am not talking about the accelerating phase of the particle. I am simply talking about the portion of the particle once it has achieved the uniform velocity. Okay. So corresponding to that, your terminal velocity of the spherical particle will be gd square delta rho by at. Okay. And if you calculate the vorticity at the surface of the particle, so vorticity at the surface of particle zeta s is equal to 3u sin theta by 2. So whenever I am talking about the surface of the particle, then r is already substituted equal to a. So that's why in this formulation you are only able to see the variation of theta but not the variation of r. Is this point clear? All are clear with these points? So basically in the previous slide, what I have done, in the previous slide I discussed the case if you have a solid particle present in, and over that fluid is moving at uniform velocity. Now I have, when I defined the terminal velocity, I considered just the opposite situation, that I have a stagnant fluid and particle is actually falling. So terminal velocity of that particle is actually shown over here. Okay. Now what I can do, I can actually see how the path is moving. So if you draw different streamlines relative to a fixed sphere, relative to a fixed sphere means sphere is actually fixed in the frame and flow is moving over the sphere. So corresponding to that, you can see these are your actually flow streamlines, and here this is your corresponding. So left side I have Stokes flow, in the right side I have nothing but the potential flow. So what I am trying to do here, I am trying to make the actually comparison of the Stokes flow and the potential flow. So one important thing you can see, when I am having these different streamlines from this point to this point, whenever I am coming here, distance between the two streamlines is actually decreasing. Okay, so what happens when distance between the streamlines decrease? There is increase in velocity of the flow. Okay, and so this is happening when we are close to the surface, but away from the solid particle, the streamlines are almost having the same gap. So it means their velocity is almost remaining constant. But if we compare the corresponding potential flow theory, so this conclusion is valid there also. So they are also close to the surface. You can see very close streamlines, and away from the surface gap is actually increasing. But one small comparison we can make, that when we are considering the Stokes flow situation, then the gap between the streamlines is decreasing, but it is not decreasing to very large extent. On contrary, in inviscid flow situation, the gap is actually decreasing too much. It means two streamlines are coming very close to each other. So it means that above this top point of the surface, in case of inviscid flow, we will be experiencing extremely high velocity. On contrary, in case of the creeping flow situation, velocity increase will not be much. Okay. Then second situation can be corresponding to this second scenario, where I have a stagnant fluid medium, but particle is now penetrating into the fluid medium. Okay, so once particle is penetrating into the fluid medium, so their nature of streamlines changes completely. So in case of Stokes flow, you will be finding that when this particle is penetrating, it is trying to move the fluid in forward direction ahead of this, and also it is imparting some motion in the backward direction. On contrary, in case of potential flow, what is happening? When particle is moving, it is displacing the fluid, but that fluid motion is actually not being carried forward in the direction of motion of the particle, but it is just creating some recirculation and once again attaching to the particle. Okay, so it means that if you have low viscosity fluid, extremely low viscosity fluid, in that case, if your particle moves, then what happens? The fluid which is just in the front of the particle, that gets displaced and once again, by following a circular path, gets attached to the rear end of the particle. Okay. On contrary, if your particle is moving in a high viscous fluid medium, there what will be happening? This type of long recirculation will not be existing, but some fluid portion will be kind of attached to the particle, which will follow it from the rear side, and the fluid in its front will be actually getting moved almost in the similar direction. Okay, so that is something which will be happening. So basically, what is viscosity is doing? Viscosity is increasing the response behavior. So distance up to which actually fluid is getting sense that okay, there is some field which is getting attached to the particle. Is this point clear? So viscosity is kind of increasing the sense in the bulk fluid that my wall is approaching the fluid. So because of that, it is already taking some advancing effect to move ahead. Okay, so it means if you have low viscosity fluid, then your this effect of wall will be felt to lesser distance. But if you have high viscosity fluid, then effect of wall will be felt to larger distance. Is this one clear? So that is something which we can compare from these two particular points. Now, instead of this solid particle, if I have a fluid particle, okay, so it means that now my particle will not be purely rigid. So particle can also have relative motion at its different locations. Okay, so once particle is having different motions, then what will be happening? We will be having other than the kinematic boundary conditions, now dynamic boundary conditions will also come into account. Okay, so if say we say that within particle also some motion is happening. So we have now relative velocity in between this motion and outside motion. So if we have some relative motion, then ultimately what will happen? There will be interfacial shear. Okay, and at the same point of time, if inside also I have a fluid, so this fluid will be applying certain amount of pressure and viscous stresses. Okay, viscous normal stresses from inside, and outside also I will be having certain pressure. So this difference of pressure, it means the forces which are acting normal to the interface, these also should be actually taken into account. Because if these forces are not considered, then we cannot ensure that the shape of the particle can remain same. Is this point clear? So now in place of the solid particle, we have the fluid particle. So we have additional complexity that along the interface of the particle we have to actually balance the tangential and the normal forces. So these two additional boundary conditions we have to actually satisfy. Okay. So considering this, again same thing is there. So you can see this E symbol is nothing but replacement of symbol delta only, because these equations are taken from different texts, so that's why the nomenclature is also coming from different books. Okay, so now one important point you can see, whenever I am writing this equation delta for psi is equal to 0, I am not writing it solely for continuous medium. I have also written psi p. So it means that within the particle also there will be some flow field. So I have to define psi for both particle as well as for the surrounding continuous medium. Okay, so this solution was independently done by Hadamard and Rybczynski. So these two persons have initially done this solution independently. Okay, but it is commonly now joined with their name, because this solution they have done almost at the similar times. Okay, so in this solution now what I need to do, my first boundary condition is when r is approaching to infinity, then I know the value of psi. So this is nothing but coming from the previous slide only. Okay, so previously also we were having this velocity, because at sufficiently away from r we are knowing the value as u. Okay, then this is second boundary condition. So from where this boundary condition is coming, can you tell me? At r equal to a, psi and psi p are equal to 0. So from where this boundary condition is coming? Again, we are making this assumption that my shape of the fluid particle and its volume is remaining conserved. Okay, so if shape of the fluid particle and its volume are remaining the same, it means there is no flow across this. Okay, so if there is no flow across this, what I can do, over this surface, over this interface, I can put a fixed streamline, and that streamline can be assigned some value, constant value. So that constant value I am assigning as equal to 0. So whenever I am looking from outside, this streamline I am calling it as psi. If I look from inside, then I am calling this as psi. Is this point clear? So this is the second boundary condition. Now these two are nothing but kinematic boundary conditions. Then we have to account for third boundary condition. So what is this boundary condition? This is coming from no slip and impermeable. Not permeable, impermeable. Okay. So this is no slip and, so this is only impermeable. This is only impermeable boundary condition, because I am writing derivative in terms of, derivative is in terms of r, so it means it is a, if derivative is in terms of r, it means what I am talking about? Radial direction or tangential direction? tangential direction. So it means if it is a tangential direction, then it is a no slip boundary condition. Is this point clear? So once I am referring to radial direction, so basically u theta is nothing but del psi by del r, proportional to del psi by del r. So that's why I am calling this as a no slip boundary condition. Okay. Then this is my next boundary condition, which is, what is this boundary condition? Tell me now, you should be able to predict. Let me give you one more term. Say K is nothing but viscosity of particle divided by viscosity of the continuous fluid. So this is K is viscosity ratio. So if K is viscosity ratio, then can you tell me what is this boundary condition? This is nothing but tangential stress balance boundary condition. Okay. So in case of tangential stress balance, what happens? Shear stress of the particle, which will be having mu p over here, minus shear stress of the continuous medium, which will be having mu over here, that will be equal to 0 if I do not have any gradient of surface tension present across the interface. Is this point clear? If I have some gradient of surface tension present along the interface, then I have to equate that equal to that particular point. Okay, so what we had done? We had done tau particle minus tau continuous medium is equal to del S into sigma. Okay, so here del S was nothing but, what was del S? Spatial derivative along the surface. Okay, so if I am saying that spatial derivative of surface tension coefficient sigma is equal to 0 along the surface, it means at each and every point along the surface I have the same value of the surface tension. When this same value of surface tension we will be having when there is no temperature and concentration gradient at the free surface. It means I don't have any variation of temperature along the surface, and I don't have any variation of any surfactant or impurities along the interface, because when impurities are present at the interface, then these changes the value of the surface tension. So it means I have contamination free system. There is no impurity, no surfactant present at the gas liquid interface. Is this point clear? Now, can you tell me what else we need? Do we have sufficient boundary condition, or can I write one more? एक और लगे. Why? I have this as 1, this as 2, this as 3, this as 4. So I have 4 boundary conditions. So it means with these 4 boundary conditions I can solve this system of equations. However, to satisfy that my shape should not deform, I should have one more balance, and that particular balance will be of normal forces. Is this point clear? Normal forces at the interface, because when shape of the interface does not deform, when I have balance of tangential as well as the normal forces. So if I write normal boundary condition, can you write now from our previous lecture how I can write the balance of normal forces? Can you write? You can only write if you have notes. If you are not making notes, then you will not be able to write. So let me show you. So this is pressure. Then along with the pressure, what I will be having? This is normal stress because of the viscosity. Normal stress because of the viscosity, or in other words I can say normal component of deviatoric stress tensor. Okay. that is equal to pressure of particle minus normal component of viscosity induced stress, and this difference of this minus this will be equal to pressure because of surface tension, which is 2 sigma by A. Okay, and this will be applicable at gas liquid interface, so that's why at R equal to A. Okay, so it means there is one interesting fact that even if I don't consider this equation, then also I am having sufficient number of boundary conditions to solve this particular problem. Is this one clear? But what I will do, because if I consider this fifth boundary condition, then ultimately what will be happening, I am having some pressure field also associated. Okay, so it will complicate the process of solving the equation, because I will be having addition of one more variable. But if I see other 4 boundary conditions, all are involving psi, and my governing equation is also purely in terms of psi. So what I will do to solve this system, I will simply consider this governing equation and these 4 boundary conditions, and then I'll solve this. So once I solve this system, what I get is psi is equal to minus ur square sine square theta by 2 into 1 minus, here I am having one simple addition. Now psi is function of r, theta, and I am having one more variable, that is k. What is k? K is nothing but viscosity ratio. Okay, because if you have different fluid combinations, then viscosity of the particle and viscosity of continuous phase can be different for different fluid combinations, and depending upon that your value of k will be different. Is this one clear? Now, similarly what I can do, I can also solve this equation within the particle. So if I solve within the particle, then whatever the solution of psi I will be getting, that I will be writing as nothing but psi p. Is this one clear? So psi I am solving outside the particle as well as within the particle. So within the particle it will be psi. Okay. Okay, if I have these two, then how can I find pressure?
Using the fifth condition.
Can I find pressure?
Fifth boundary condition.
Yes, using fifth boundary condition. So one thing is I can calculate pressure using this fifth boundary condition. Other than this, can I find pressure using some other way? Yes, again I can go back to my momentum equation, and from momentum equation also I can find the pressure. Okay, why I am saying this? Because now here we have one very important conclusion at this point. So one pressure I can calculate from momentum equation, and one pressure I can calculate from the fifth boundary condition. Is this one clear? Now one important conclusion is that my surface tension pressure was considered in which boundary condition? Fifth boundary condition. Okay, surface tension force was considered in the fifth boundary condition, and all other 4 boundary conditions nowhere involved value of surface tension. So it means that, but still whatever the solution we are calculating, the solution we are calculating by subjecting boundary conditions that I don't have any flow across this interface. So if I don't have any flow this interface, it means my shape of the particle is actually remaining intact. So it means that for smaller particles to be of spherical shape, surface tension does not matter. Whether your value of surface tension is small or large, irrespective of the surface tension, shape of the particle can stay as spherical. Is this one clear? What I am saying, is this making sense? And at the same point of time, whatever the pressure we are calculating without considering the surface tension, and with considering the surface tension, if both the pressures are actually matching, then ultimately I can say that the pressure which is considered without including the surface tension, if that pressure distribution is matching with surface tension, it means that surface tension is not then leading to any change in shape of the body, shape of the fluid body. Are you getting this point or not? Let me repeat it again. This is important conclusion. So whenever we have solved this biharmonic equation, this biharmonic equation I have solved by using the 4 boundary conditions. Okay, and all these 4 boundary conditions nowhere involved the surface tension, because surface tension boundary condition was coming as over specified, and that was not needed in order to solve the solution of system of equations. So it means that, and particularly whenever I have specified the 4 boundary conditions, in these 4 boundary conditions, one assumption I took that my fluid particle cannot, any fluid medium cannot penetrate through this, and also streamline is actually fixed to this particular interface. Okay, so it means shape of the interface is not deforming and no fluid is crossing across this. So it means this shape of this spherical shape of the fluid particle is also being satisfied without inclusion of the surface tension also, if I have a creeping flow situation, if I have a viscous dominant flow situation with smaller size of particles. All are clear with this idea? And whatever the surface tension force is coming, that is also actually helping in maintaining the shape. But if you say that you have smaller fluid particle present in the surrounding continuous medium, even if the gas liquid pair has 0 surface tension, then also shape of the particle will remain spherical. So this is the important conclusion which we can actually make from this point. Okay, because without solving the pressure also, my spherical shape, because if you draw the streamline pattern, then you will be finding your streamline outside are like this, and within the particle your streamlines are like this. Okay, so always if you have a contamination free system, it means a system for which surface tension value at the entire gas liquid interface is constant, for that particular system, within the drop or within the bubble, so fluid particle either it can have a gas medium inside or it can have a liquid medium inside. So any fluid particle, whether it's a drop or a bubble, it will be having this type of recirculating patterns. So here you can see. So when the flow is moving in this direction, so here tangential velocity has to become same. So because of that, this tangential velocity is actually moving across this, and from this side also tangential velocity is moving like this within the bubble, and at the center actually these are turning back and forming a internal recirculation pattern. So it means when smaller bubbles or drops penetrates through the surrounding viscous medium, then we have always internal circulation within that. So it means that this fluid medium is not remaining rigid. We have relative motion between the fluid particles because of the circulation pattern within the bubble. All are clear with this point?
Sir, but we assume that fluid is stationary.
Fluid is stationary means?
The continuous medium and bubble is just.
Yes. So if you take the other situation that your surrounding continuous medium is stationary and bubble is rising. So once bubble is rising, it will displace the surrounding continuous medium ahead of that and behind that. So that displacement will actually be coming in the form of this type of streamlines. Okay. So it means you can have two situations. Either your bubble is just standing at this point and flow is moving like this. So if flow is moving like this, though bubble is standing at this point, but within the bubble medium there are continuous recirculations. Or in second sense, you can say that bubble is moving at uniform velocity. So within the bubble there is recirculation. So bubble is moving also, and within the bubble also there is recirculation, and then in the surrounding also it is imparting this type of motion. Okay.
Bubble will do circulation, single circulation.
Single bigger, because this is the mathematical solution. You plot these streamlines, you are getting these two circles. You have solved the biharmonic equation which is applicable for this solution, and this biharmonic equation is actually forming streamlines like this. Okay. And physical reason, if you want to understand, then what you can say is that flow is moving like this. So if flow is moving like this, within the bubble and outside the bubble you will be having velocities same. If velocity is same, tangential velocity is same, then fluid medium within the bubble will try to move like this. From here also medium will try to move like this. Once two mediums are flows is coming from this side also, this side also. Once it will be striking, then what it will be doing? There is continuous feed from the back side. What will happen? It will bend. It will try to take the least resistance path. Of course, it cannot cross the boundary of the interface. That is the condition we have taken. So what it will do? It will try to recirculate like this. Okay. So here you can make the comparison for different values of viscosity ratio. So K is 0. So K was nothing but mu P by mu. So mu P is particle viscosity by. So K0 means your continuous phase viscosity is extremely high in comparison to particle viscosity. So you can consider this like a air water system. Okay, so say you have air bubble and outside you have water as liquid. So then air viscosity is very low in comparison to viscosity of the water. So you will be having this type of system. Okay, so if you increase the value of K, then what is happening to your flow field actually? That is shown over here. Okay, is this one clear?
What is shown here?
Can you see what is happening? Can you observe these streamlines and then tell? If you see this portion, so internal circulation pattern is almost same. Okay, but if you see outside what is happening? This gap is actually more widened in comparison to this gap. Okay, so you have different surface curvature upon change of this, upon change of the viscosity value. Okay. You use different fluid pairs. First you take air water system, then you take air glycerine, then you take any other fluid medium, immiscible fluid medium. Just change the properties between the fluids. Okay. Then so this was for a fixed particle and flow is happening over the particle. If you have other situation where your particle is actually moving and in the surrounding you have stagnant fluid, so then you will find streamlines something like this. Okay. Then one interesting point. Now what we need to do? We need to calculate again the drag forces. Okay, so here if I calculate only first form drag I can calculate from pressure distribution. Okay, and then if I write that form drag divided by half rho u square, that will be nothing but my CD. So this I am calling as form drag coefficient. So this is my CD1. So CD1 is now having one addition of K also, viscosity ratio also I am having in account. Then this is CD2. So CD2 is nothing but it is normal component of viscous drag. Viscous drag due to normal stress. Viscous drag due to normal portion of normal component of deviatoric stress tensor. Okay. Then third I will be having purely because of the shear. So that is viscous drag due to shear component. Okay, so viscous drag due to shear component. Okay, now my total drag coefficient will be something like this: 8 by Reynolds number 2 plus 3k by 1 plus k. Okay, and if my value of k is equal to 0, or if value of k is equal to infinity, what will happen? If my value of k is equal to infinity, it means particle velocity is infinite. So nothing but identical to a solid particle. So then this limiting case will become 24 by Reynolds number, and here this particular component will actually vanish. Okay, so I will be having only the drag force because of the this one tangential component and the pressure component. So normal stress will not be continued. Okay, this is just a limiting case, and then I can calculate also the terminal velocity. Okay, so terminal velocity again I have to balance. Yes, drag force. So sum of all these three drags. So total drag with the buoyancy force. So if I balance, then I will be getting the terminal velocity, and this will be vorticity at the surface. Now if you compare this terminal velocity and if you compare the terminal velocity of the Stokes flow, you will be finding that this terminal velocity is higher in comparison to the terminal velocity of the Stokes flow. Okay, so that is something I have mentioned over here. So you can see for fluid particle, so this Hadamard-Rybczynski theory predicts that terminal velocity of fluid sphere is almost 50% higher than of rigid sphere for same size and density. Okay, so it means typically if you use a spherical fluid particle or a solid spherical particle having same size and density, then you will be finding that fluid particle should have more velocity in comparison to that of a solid particle. And particularly, what is responsible for more velocity? Internal circulation is responsible, because that is favoring the flow direction. So depending upon the what is happening in case of solid sphere. In case of solid sphere, when fluid is moving across the interface, then fluid velocity just at the interface is actually exactly becoming, yes, relative is 0 in both cases. Okay, relative is 0 in both cases, but if you see, the particles of the fluid medium are actually moving through these vortices. So these will be favoring and decreasing the interfacial shear. On contrary, if you see in other case, there what you will be finding, particles are rigid, so there you will be experiencing the more resistance. Okay, so it means internal circulation is responsible for decreasing the drag force and increasing the velocity. Okay, so internal circulation present in fluid particles is responsible for decreasing drag force and increasing the terminal velocity. Then second point is, this is very important observation. Experimentally it is observed that small bubbles and drops tends to obey Stoke's law. So theoretically we are getting that this should have higher velocity, but experimentally whenever the measurements are done, then it was found that the value of velocity is actually more approaching towards the Stokes result. Okay, so now what can be the difficulty? Yes, if internal circulation is not happening, or there is some deviation in the internal circulation from its exact structure. Okay, so what are the possibilities of deviation? Yes, this is very important point. So whenever we have derived this solution, we considered that interface should be surfactant free, contaminant free. But in real scenarios, every time we will be finding that interface is not actually contaminant free. So once the interface is not contaminant free, then what will be happening? The internal recirculation pattern actually will be disturbed. So once we have disturbance in the internal recirculation pattern, of course, it will be actually leading to changes in the value of terminal velocity. Okay, so there are different theories, 3 different postulates which have come to explain this anomaly. So first postulate was given by Bond and Newton, and they mentioned that in case of small fluid particles, they follow Stokes' law, but when we increase the diameter, the velocity approaches towards Hadamard-Rybczynski value. Okay, so it means upon increasing the diameter, they are saying that these are approaching towards this value. So what was their hypothesis? Their hypothesis was that a circulating particle requires energy locally to stretch the interfacial area element. So interfacial area element will remain in its stretched position once the internal circulation is actually investing certain amount of energy in maintaining its free surface, so its interface shape. So once this energy is being invested, it means we will be having some additional tangential stresses. So this was the first theory, and based on this theory they found that this criteria was given the name Bond criteria, that if my bond number or Viscous number is greater than 4 for a fluid particle, then only it will be having Hadamard velocity, otherwise it will be approaching to Stokes velocity. Okay, so though this particular criteria was having sufficient accuracy, but still there were certain cases where this criteria actually was not working. Okay, what people have done some specialized experiments where they have given ultimate care to make the interface surfactant free, contaminant free. So in that pure case, actually velocity, even if your bubble Viscous number or drop Viscous number is less than 4, then also they were approaching the higher velocity. Okay, so that's why this theory, to certain cases, this was not actually working. And in certain cases, what people have done, people have actually added the impurities from outside, and they have added such impurities which are not actually changing the surface tension. For example, some known solid particles were added, and these solid particles were added which cannot change the value of the surface tension. Okay, so with these particles it was observed that there is no change in the value of viscosity. So it means size is not a strong criteria. So that's why then it was concluded that Bond criteria is not always applicable for all cases. Okay, then subsequent research was done, and then Bozanic proposed that lack of internal circulation in fluid particle due to interfacial monolayer. So it means at the interface we have formation of some viscous layer which is allowing very close to the interface, some particles to remain stationary. And only surface tension cannot explain the complete interface rheology, but some additional viscosity should be accounted for, which is called as surface shear viscosity. Okay. By considering this surface shear viscosity, what they have done, they have given the value of terminal velocity. So this was identical to that of the Hadamard relation. Only one addition was C by mu. Okay, where this C is nothing but equal to the surface dilatational viscosity divided by 1.5 times the radius. So C means some factor which is accounting for the viscosity, additional viscosity layer at the interface. So this was second theory, but this theory has not become very popular because the issue was it is not very easy to determine surface shear viscosity. Okay, so surface dilatational viscosity is not very easy to calculate. So that's why this theory was again not popular, and so it was difficult to make reliable measurements for the surface dilatational viscosity. So that's why another theory came which mentioned that if we have some surface active substances present on the interface, then these substances tend to accumulate at the interface, rear portion of the interface, thereby reducing the surface tension. So it means if you have some particle present in the medium, and typically if particles are such that these are not soluble in the bulk fluid medium, so ultimately where these particles will settle then? These will settle at the interface. So if you have some particle within the fluid medium which is not soluble in the fluid medium, so these will try to move away from the bulk of the medium. So once these are trying to move away from the bulk of the medium, these will get accumulated at the interface. So once you have some system where you have some particles which are collected on the interface, okay, and if this drop now started moving in the upward direction, so what will happen? These leading particles will be displaced to the rear end. So you will be finding that the top portion will be particle free, pure, and in the rear portion you will be having accumulation of the particles. Is this point clear? So if you have some particles which are collected on a stationary interface, once this interface started rising in the upward direction, so leading edge of the interface will have some recirculation. So because of that recirculation, this particle will mostly accumulate near the back portion. So now in this top portion will have high surface tension and back portion will have low surface tension. So it means if you have this difference of surface tension, it means then in our theoretical analysis, whatever the term in one of the boundary condition delta S sigma we made 0, that is not a correct assumption. We have to account for that variation of surface tension. Okay, so that's why it was found that these surface active agents, these are swept to the rear portion and leaving the frontal portion relatively uncontaminated, and the gradients are more pronounced in small bubbles and drops in comparison to the larger bubbles. So whatever the gradient of the surface tension because of the accumulation of the particle is happening, that is not much stronger in the larger particles, but in smaller particles these gradients are actually more stronger. So that's why smaller particles, because of this gradient of surface tension, they are actually trying to slow down, okay, and they are trying to approach the velocities close to the Stoke's design velocities, okay. And so surface contamination theory tells that for all bubbles and drops, no matter how small, we will be having internal circulation if the system is sufficiently free from contamination. So what people have done, as I told you, that when people tried to include make pure contamination free system or include some particles which are not interfering with the surface tension value, for all these cases people were able to see the formation of symmetric rolls, okay. But when contamination was introduced intentionally to the system, it was found experimentally that if say this is moving in the upward direction, your roll formation is something like this. So it means here you have some stagnant fluid portion near the in between the fluid particle. Okay, so fluid particle is having recirculation, but that recirculation has deflected from its rear end, and that recirculation is actually bending something like this. Okay, and you have some portion behind this bubble where there is actually stagnant fluid. So basically that stagnant fluid is something which is responsible for the increased forces and which is leading to retardation of the bubble velocity. Okay, so how this surfactant effect can be taken into account through mathematical analysis, that we will discuss in the next class. Okay, is this one clear? So we can actually take into account this also through some mathematical equations that we will discuss in the next class.